streaming is working. Once I know it's working, I can close it. Alright, so the streaming is on. We are currently streaming to YouTube already, and it's time to get the class started. So I'm going to get started here. This is my usual way, well, it's becoming my usual way of starting a class, which is starting with a mind map to kind of remind people that, it's important to review current concepts, and there are a lot of current concepts. So at some point in time, I would not be able to spell out, what concepts are currently already covered. So at this point, we have just gotten the set operations done, so intersection, union, that sort of stuff. But more importantly, we also have talked about quantifiers. So those are all very important concepts to understand at this point of time, because what we'll be talking about today is going to depend on both set concepts as well as quantifier concepts. So that's why it's really quite important to make sure that we kind of clear away all the new concepts and all the basically new definitions as soon as we get those. As to new concepts, what we'll be talking about today, the first one we're going to talk about is to kind of go back and talk about Cartesian products, because that's one thing that we haven't talked about yet. I have some examples here, but they're also in the notes as well. And then after that, immediately after that, we'll talk about functions, because functions are essentially a subset of the Cartesian product between the domain and the codomain. So we'll get to that. When we get to that, we'll start to understand what is the domain and what is the codomain. So with that said, I'm not seeing any questions in the text channel, and you guys already know that you can post questions in the text channel anytime you have questions. So don't hesitate, just kind of keep those questions coming in the text channel as you have questions. So what we'll do now is kind of go back to module 0280, which is the basic set theory module, my module, not the Canvas module, and talk about what is Cartesian product, which is right here. So what looks like A times B, using the cross symbol for multiplication, that's the Cartesian product. Which is not unlike certain operations in linear algebra, but since linear algebra is not a prerequisite of this class, I'm not going to use those. So the abstract description here is A Cartesian product with B is going to be a set. Now how do we know that? Because the result has the set enclosure type of notation, which is the open and the close brace. Now, what would the elements look like in the set, which is the result of the Cartesian product? So each element is going to look like this, in parentheses xy. So this is a new concept. It is called a tuple. So each element in the Cartesian product is going to be a 2 tuple. So when we say it's a 2 tuple, it means it is a tuple that has 2 elements. Now, when I use the word tuple, it's really just the mathematician's version of an array. Okay, so that's basically what it is. Okay, it's really just an array. So in this case, every element is an array of 2 elements, where the first element has to come from A, and then the second element has to come from B. So that is the definition of Cartesian product. And that's about it. I mean, that's really it. Okay, that's the definition of the Cartesian product. So now we want to kind of look at some examples, which is there's one in the mind map. So if I go magnify a little bit, you can see there's an example here where I use one set, which is 1, 2 as a set, and then another set that has ABC in it, and I try to make a Cartesian product out of it. So in this case, the outcome, the result of the Cartesian product, is going to be a set of 2 tuples, where each 2 tuple has the first element coming from the first set and the second element coming from the second set. So you can see how when we do a Cartesian product of 1, 2, and ABC, we end up with 1A, 1B, 1C, 2A, 2B, 2C. So do we have any questions about the example that we are looking at here? All right, I'm not seeing any questions. So what I'll do is I'm gonna talk about another example, which is going to be a little bit more. I will say it's a little bit more tricky. Okay, so we'll go ahead and take a look at this. So I'm actually typing in LaTeX format as we go, just so that you guys can get an idea of how the notation is being entered above. So this is times, and this time we use an empty set. So I will ask you, what is that? What is the result of this particular Cartesian product? I'm separating the question and the answer, because this way you can actually see the finished version of the question instead of just seeing backslash LaTeX, dollar sign, blah blah blah. Okay, so I want you guys to think about it. Okay, and Wade is right. Okay, very good. So Wade is correct. So the answer is, so I'm gonna use LaTeX. The answer is the empty set. But why, right? Why is the answer the empty set? Because the result of the Cartesian product should be two tuples, where the first element comes from the first set, which is the set of 1, 2, and the second element has to come from the second set, which is the empty set. Then you go like, but the empty set has no elements, so it's impossible to define a two tuple in this case, because the second set has nothing in it, and that is why the answer is the empty set. All right. And Wade is typing something in the text channel. I'm keeping an eye on it. And so is Elijah. All right. Oh, okay. All right. So Jonathan is typing too. So we got a few people typing. I was told that, the tuple order matters, but the order of tuples in the set do not matter. That is correct. So in this particular case, you can reorder the items inside the set any way you want, but you cannot reorder the elements inside a tuple. So what I mean is, if you want to list 1b before 1a, that's perfectly okay, not a problem. Okay, as long as we still have those exactly the same 6 elements in it, that's okay. However, you cannot exchange the ordering of items within the two tuples. So 1a and a1 are considered distinct. They are two different elements. So very good. And then the next question is, would it be one empty? No, it is just empty set itself. Okay, so in other words, if I were to make this more clear, the answer is just the empty set. It is not a set of an empty set. It is the empty set itself. And somehow, I see, because I forgot to use an open dollar sign here. And there we go. All right, so that should answer Elijah's question. And then Ahmad is asking, is there a containment in set theory that allows for duplicates? I think I mentioned it's called a multi-set, but we do not use the concept of a multi-set in this class. And then Tosh asked, is that correct? That is correct. All right. And sets where order doesn't matter. Well, order does not matter anyway. That's the whole concept of a set, is the order does not matter. So I think what you meant to ask was where the order is important. That would not make it a set anymore. All right, next questions come from Nathan. And Nathan's answer is correct. So the Cartesian product between the set of 1, 2 and the set that has an empty set as an element is going to be a set of 2 elements. Each one is a 2 tuple. One empty set is 1 2 tuple, 2 empty set is the other 2 tuple. That is correct. Nathan, you're correct about that. Um, all right. Yes, tuples do allow duplicates, but sets do not. Yes, so Adam is correct because it is an array. You cannot say an array cannot have duplicate items because when you okay, let me just write it here. So that's an important concept. So let's talk about tuples. So what do we know about tuples? Okay, ordering inside is important, and then the second one is duplicate items are fine. Okay, so let's use some examples. Okay, so we'll take a look at 1 2 and 2 1. So those two are not the same. So I'm going to use the LaTeX notation to put in a not equal to symbol. So 1 2 as a 2 tuple is not the same as 2 1 as a 2 tuple. Another example. Okay, so we'll say 1 1 is a valid 2 tuple. So it's perfectly okay. It's fine to have the first element in the tuple and the second element of a tuple to be the same. So there's no rules as to whether values or elements inside a 2 tuple can be the same or not. So there's simply no rules about that. All right. Okay, cool. All right, any other questions about tuples? So tuples are important because this is the format of elements inside a Cartesian product. So we still got a few questions coming in, so I'm gonna pause, in terms of the lecture material, because I want to make sure that all the answers are answered before we go forward any further. Alright, so here is no question about the tuple, but I don't understand why the Cartesian product of an empty set is, or if any component of a Cartesian product is the empty set, then the outcome is going to be an empty set. So I'm going to challenge Chris to figure out the Cartesian product of this particular example. What do you think is going to be an element in this particular Cartesian product? Because if Chris is asking that question, it kind of implies that there are situations that he thinks that it is possible to have a non-empty set as a Cartesian product when one of the set that we're operating on is an empty set. Exactly. So Jonathan is right, but it is a very kind of weird concept because you cannot have a 2 tuple that only has one element and say, well, since there's nothing in the second one, so we'll just leave the second element of the 2 tuple empty. We cannot do that. Exactly. One nothing does not work because there has to be a second element, and that second element has to be an element of the second set where we are operating on. So that's why when one of the two sets that we are trying to find a Cartesian product of is an empty set, then the outcome, the result of the Cartesian product has to be an empty set. It's kind of like, something multiplied by 0. It's kind of like that. Okay, we still have some typing going on, so I'm going to pause and we'll make sure that all of these concepts are clarified before we go any further. And now alright, so Wade said, and you can think of tuples as functions. Well, okay, hold that thought. Hold that thought. We're going to get to functions. We're going to get to functions. Even if you don't have a narrowly defined function definition, any element in a tuple has a fixed ratio to the rest of the tuple's elements. I'm not really quite sure what that means. The last part of the text message. Any given element in a tuple has a fixed ratio to the rest of the tuple's elements. In the first example, Tech gave there is no ratio from 1 to A or 1 to B. I'm not really sure what what that means. You can kind of imagine rows and columns, right? So if you think about, the first set is responsible for columns, and then second set is responsible for what did I say? The first set responsible for columns, and the second set is responsible for the rows. Then you have a table, right? And then each item, each cell in the table would take the first element coming from the column, and it would take the second value coming from the row. So when one of the two sets is empty, then you have either no row or no column. So that means your table is going to be empty. So there you go. Position and numeric values are static. They are simply just notations, representing values that we can put into a set. That's all. Okay. Yeah, they don't have to be numerical value. I mean, you can definitely have something that is non-numerical. I'll give you an example where things are non-numerical. It's going to be a fun example. Alright, so we'll have this particular example. Okay. So we'll have MX5, let me see, 750. So these are models for cars. Okay, MX5 is a Miata, is the same as a Miata, which is a Mazda, and the 750 is the BMW 750. And then the second set would be people. So that would be me and a friend of mine whose name is George. Okay. So in this case, the end result is going to be, all the possible ways to pair up the cars with the people. So you have MX5 paired up with Tack, and then you have MX5 paired up with George, and then you have BMW, the 750, paired up with Tack. Whoops, let me see. Nope, that's correct. Okay, I was just making sure that the ordering is correct, because the first item in the two tuple has to come from the set on the left-hand side of the Cartesian product operator. So now we have the second one is, nope, I think, oh, we have George. Okay, so there we go. So that's another example of using Cartesian product. It's not limited to values or numbers or just letters. It can be anything. All right. So Jonathan is making an observation. Yes. Okay. So in fact, based on Jonathan's observation, this is not exactly, I wouldn't call it a rule, but it is a result of how the Cartesian product is defined. So the cardinality of the Cartesian product between two sets, we'll call the two sets x and y, is going to be the same as the actual cardinality of x times the actual cardinality of y. So this is a good observation, because it really is true. Okay, you just have to count the number of items in x, and then you count the items of y, and when you have a Cartesian product between those two sets, then the number of elements in the Cartesian product is the actual product, as in multiplication, between the cardinality of x and the cardinality of y. Now, that being said, it gets a little tricky when the number of elements in x is infinite and the number of elements in y is also infinite. So if you think about x as the set of all integers and you think of y as the set of all integers, then you go like, that is going to be pretty awkward, right? Because there's no infinity. I mean, infinity does not equal to infinity. You cannot compare infinity to infinity. Infinity is a concept. It is not a value. It cannot be compared to. So we'll get to that question later. Okay, how do we compare, the cardinality, or how do we compare two sets, where they both have an infinite number of elements? I will not quite, okay, not quite indeterminate. Sometimes we can actually establish a equivalency. So I will give you a kind of a preview, okay. This is something that we'll talk about once we are done with all the concepts of functions. So, but I do want to get you guys to start thinking about it, okay? So think about the set of all natural numbers. Natural numbers, some people say it starts with 0, some people say it starts with 1. It doesn't really matter, okay? So if you think about all the natural numbers, 0, 1, 2, 3, 4, 5, 6, and so on, and then you think about the set of all the integers, okay, which can go positive and negative, right? So 0, positive 1, negative 1, positive 2, negative 2. Those are all elements of a set of integers. So I'm going to ask you, how do we compare the cardinality between those two sets? How do we compare the cardinality of the set of all natural numbers versus the cardinality of the set of all the integers? Okay, so hold that thought for maybe a week, okay, because we'll answer that question. It's going to be a fun question to answer. Decimal numbers is not too bad, okay. If you have a fixed number of digits, it's pretty easy to deal with. It's when we get to irrational numbers, then we have a little bit of a problem, okay. So rational numbers, including fractions, not a problem. We can deal with those. But once we get to irrational numbers, then we go like, things gets a little weird. Alright, so that's all I have to say about cardinality, because that's how cardinality is defined. And now we are moving on. Okay, let me see. There's a comment here. The set of rationals is the same as the set of naturals. Yes, the cardinality thereof, yes. Which is kind of weird, okay? And even if you think about coordinate systems, okay? So think about your screen, okay? The screen that you're looking at right now, okay? And you can think about that screen being infinitely large, okay? Where each pixel has a x and a y coordinate. So if you think about all the possible xy coordinates of a screen that is infinitely large, and you compare the cardinality of that set versus the cardinality of the set of natural numbers, most people would naturally think the two-dimensional space is going to have a larger cardinality compared to a single-dimensional space. Now, since I said that in this particular way, you already know the answer is nope, they are actually considered the same. They have the same cardinality. So after we talk about everything about functions, we'll get to that concept, okay? It's called Aleph No. So we get to that concept after we are done with all the discussion about functions. Exactly. I think it is fun, but apparently, quite a few people disagree with me, then say, no, Tak, this cannot possibly be fun. You're weird. All right. So functions as sets, okay? And the first few things we have here is to reintroduce tuples. So in order to describe a function as a set, we need to utilize the concept of tuples, and it points back to the module that we already visited, which is 0280. A tuple in general is an ordered container where its components are ordered and the ordering is significant. Furthermore, a tuple can contain duplicate items. The tuple 112 is considered distinct from the tuple of 121, even though both only consist of ones and twos. Well, one single two, but two ones. A tuple is represented by a comma-separated list of items enclosed in parentheses. So you have to make sure that you use round parentheses and not brackets and not braces. So ABC in parentheses is a 3 tuple. The 3 refers to the number of items in the tuple. given T is a tuple, sometimes we can use the array indexing operator, because after all, this is a computer science class, right? So we kind of like to borrow, from the notation where we already know. So in this case, I use the square bracket for indexing so that we can refer to a particular element inside a tuple, just like an index into an array in CISP440 or in just about any programming language, except for Visual Basic. Yeah, Visual Basic likes to use parentheses for indexing, where everybody else use square brackets. All right. So now we are moving on to functions. So the first thing I need to clarify, because all of you have taken pre-calc, because that's the prerequisite for this class. When you think about functions, you're thinking about, sine, cosine, that sort of stuff, okay? No, not in this class. We're talking about something that's similar, but not really the same thing. So, because in those other classes, we're talking about functions that are quote-unquote continuous. Because x is usually, when you're in a math class, x usually comes from the set of irrational numbers. So it's continuous. So that means you can say, f of e, the natural log constant, is 2 times e. Okay, well, kind of makes sense. Okay, not a problem. But in this class, we look at it in a slightly different way. So I want to kind of talk about this first, because I want you guys to kind of shift, how you look at a function from what you already know in your math class, and also what you know already in a programming class, to the strange way that we are defining functions in this class. And we're going to use this concept, the concept of a function defined like this, all the way throughout the entire semester, all the way to the very end, when we'll be talking about Dijkstra's algorithm and the A-star algorithm. We'll still be using functions exactly the way as functions are defined at this point. Okay, so that's probably a good thing. It's probably a good thing for you guys to really make sure that you get the concept of a function, because it's very, very useful in this class. So we start with this notation, f and then a colon, and then x is a set, that's why it is an uppercase. F is a set too. We'll see that f actually is a set as well. And then we have a right arrow, single arrow to y. So I use a single arrow here because we already use a double arrow for implication. So I'm going to use a single arrow here. So the way we look at this is f is a function where x is the domain and y is the codomain. But Tack, what exactly does it mean? Well, it means this is a mapping. Okay, f is a mapping from the set of x to the set of y. All right. Well, what does that mean? Well, the first thing we want to talk about is, so we'll go ahead and reuse the example. Unlike many other math classes, we also view a function as a set, which is exactly what I said. Well, not what I said already, but I'll be talking about that. A function is a set of 2 tuples. Okay, let's focus on this one here. A function is a set of 2 tuples. But Tack, didn't you just kind of mention something about, a set of tuples, and I believe that concept was the Cartesian product of 2 sets? Well, I'm glad if that is what you're thinking. That is good, because you're relating something that we just talked about to something that we are now talking about, and those two are indeed related. So we'll consider a concrete example, which is f of x is 2x. I mean, this is something that you guys all know already, because you can plot a line, right? Because if you have a graph paper, you can just plot a straight line and say, oh, this line here is representing f of x equals to 2x. But in our class, it is a little bit different. So first of all, we have to identify the domain. What values are we mapping from? And the domain is a set. So let's just say that we're only interested in integers. In this class, it's called discrete structure. So when we use that term discrete, we are talking about something that is quote unquote countable. Okay, And we'll talk about what is countable later on, because it's a concept that we don't have enough vocabulary to explain that concept at this point. But we'll just say that we're interested in integers. The set of integers is also, it has a symbol that looks like a z, but it's not exactly a z. It has kind of like a double bar, across the diagonal line. The codomain is a little tricky. We'll also assume the codomain is also z. So in other words, in this case, okay, if we just look at it from the perspective of domain and codomain, then f is going to be a function mapping from integers to integers. All right, so now the question is, how do we see it as a set? We see it as a set because this is how we describe the content of f as a function. So f in this case is a set of two tuples, where the first item of each two tuple is coming from the set of integers, and the second one is also coming from the set of integers. And we can see how 0 times 2 is 0, 1 times 2 is 2, 2 times 4, 2 times 2 is 4, 3 times 2 is 6, and so on. So we are essentially spelling out the mapping between the domain and the codomain. Let me pause here and make sure that we don't have any question before proceeding, because this is a new concept. Okay, we are no longer looking at a function like a continuous line that you normally see in a pre-calc class. We are looking at a function as a set of two tuples, where each two tuple maps a single value from the domain to a single value in the codomain. So do we have any questions about this particular concept? Because it's a shift of perspective, okay, how we look at functions. So if we have questions now, now would be a good time to ask those questions, because it's good to clarify these things before going any further. And I'm glad to see a bunch of people are typing. I'm not sure whether they're typing to each other or typing in the text channel, but there we go. Like a linear algebra transformation. Sort of. Sort of. But let's not talk about linear algebra, because that is not a prerequisite of this class. Okay, and then on is saying I think I'm lost how we have 0, 0, 0, 1, 1. There's no 1, 1. There's 1, 2, because we are mapping 1 to 2 times 1, which is 2. We're mapping 2 to 2 times 2, which is 4. We are mapping 3 to 3 times 2, which is 6, and so on. And then Victor says, so the domain and codomain is like x and y of a math function. Sorta, sort of. Except things are discrete. Okay, we are not talking about real values here. We're talking about integers. So later on we'll find what is the biggest distinction between the set of integers versus the set of real numbers. And then Wilson says, this looks like the Cartesian product of the domain and the codomain. Yep, it is a subset thereof, okay, which is explained in just a little bit. So I'm glad you guys are making the observation, and I'm not sure how many of you have read the notes ahead of time, which is kind of useful in a way, but it also makes the class less fun because you already know what I'm going to say. It's kind of like reading the synopsis of an episode of, let's say, Elementary or Sherlock, and then you watch the episode. It's like, that kind of defeats the whole point of watching that. Yeah, but I still think it's probably good for most people to read the notes ahead of time. The trailer has some of the highlights, but it doesn't show you the connections between the highlights, right? It shows you something that you say, oh, but I want to know what happened after that. Yeah. Alright, so we still have 3 people at least, typing. So I'm gonna wait until the text channel is quiet before I go forward. All right. Yeah, let's let's deal with surjection later. We probably cannot get to surjection today, but next Monday we probably can get to injection, surjection, and bijection. So hold on to that thought. All right. Next, we have pre-reading is first impression, better contextualization. That is correct. And that's why it's kind of important, especially in classes like this. When describing a function using that notation, this description doesn't give info of how the function is mapped. That is correct. All we are doing is to identify what is the domain as a set and what is the codomain as a set. That is correct. Next we got Nathan commenting on Owen's comment. The way I think of it is each tuple represents the function input and output. Yeah, kinda like that. But there's a limitation. There's a rule that we have to abide by when we call something a function that we'll talk about in just a little bit. All right, and what else? We have Douglas typing. Very good. I believe Monday is a holiday. Darn it! Okay, so Wednesday it is. Okay, which means you have a pretty long weekend until we meet again next Wednesday. So that means, it's probably a very good time to review all of the concepts and make sure that everything is solid before next Wednesday. Exactly. All right. So that really boils down to, for all x in z, which is the set of all integers, for all y in z, which is the set of all integers as well, y equals to x is a condition. It can be true, it can be false, because what we're doing is we are just I shouldn't say randomly. We are picking x, some from the set of all integers. We're picking y from the set of integers, and then we look at those two and say, does y equal to 2 times x? If that is the case, then we better make sure that x, y as a 2 tuple is also in f. If this is false, we have to make sure that x, y is not in f. So that is how we define a function. It is a set of 2 tuples, and in some cases there's a particular relationship between the first and the second item in each 2 tuple, like this one. And other times there's no such definition whatsoever. Okay, and there are some other things dictating, why we put certain things into a function. Okay, my watch just buzzed me, which means it's time to take roll. So we'll go ahead and take roll. I have to go find the window first. There we go. I got it. And let me bring that into your view so you can see the answer of today's roll taking question. And it is Cartesian. Okay, you can either capitalize or not capitalize the first letter. I'm pasting it into the text channel so you can just copy and paste. And let me double check and make sure that the due date is set up correctly. It is at 5:17. Yeah, so that's all good, right? I don't think it would take you this much time to enter Cartesian. So once again, don't try to spell it, just copy and paste it. Alright, so I'm going to move this one out again. So this way I can actually see, how many people have answered that particular question. And when enough people have answered the question, I'm going to move on. Alright, so oh, that's interesting. Wade said that's what I was talking about earlier. Yes, Control C and then Control V. Copy and paste. Yeah, certain questions I'm thinking whether I want to answer or not. And if so, how I would like to answer the question. Yes, I would assume. Alright, so I'm gonna refresh my screen that you cannot see, so I can just kind of check how many people have answered. I would say that's the majority. Very good. And now we're going to move on. So once again, for those of you who want to learn how to put in all of these, funky symbols, just right-click, show math as, and then we go to the tag command, and now you can see, the funny-looking z that represents the set of all integers is \mathbb, and then open curly brace z, and then close curly brace. So that's one way for you guys to learn how to use the LaTeX format to enter math equations. I believe that is also used in Canvas. So if you're taking a math class and your professor says, I want everything to look professional, including all the integration symbols and whatnot, once you learn how to use LaTeX, you can make everything look nice in mathematical notations. All right. Blackboard numbers, bold numbers, letters. Not sure what blackboard you're talking about, because blackboard can refer to a LMS or learning management system, which is kind of like a competitor of Canvas. But blackboard can also mean literally like a chalkboard, which is just a Oh, it's \mathbb. Yes, so I think it does work for all letters. All right, so now we're gonna get into some really abstract stuff here. All right, what makes a function a function? I know, that's really not so good of a title, but it does kind of capture what this entire paragraph or section, is trying to explain. So when I say f is a function with a domain from x to a codomain of y, even though we don't know exactly, how each element of x is mapping to an element of y, we know certain things about it already. The first thing we know is f is a subset of the Cartesian product between x and y. See, that's why, I kind of deferred the discussion of Cartesian product until today, because it is used right away. If I talk about it like a week ago, and then I say, that concept that we talked about last week about Cartesian product, f is a subset of it. It's like, what did you talk about? So now that it is fresh to us, f is really just a subset of the domain Cartesian product with this codomain. It doesn't matter. As long as we know f is a function, x is the domain, and y is the codomain of the function, this constraint has to be met. Yes. In other words, a function is a subset of the Cartesian product between the domain and the codomain of said function. That's all this thing is trying to explain. So f is really not referring to a particular function. It is simply saying if f is a function and x is the domain and y is the codomain, then this particular constraint has to be met. Are we good with this one? It simply means that you cannot have anything extra, like mapping between things that are not in the domain or the codomain. All right. So this one I think is fairly obvious. Okay, I think it's fairly obvious that a function has to meet this requirement because after all, you are mapping something from the domain to the codomain, and then each element in a function is specifying a single mapping from a single element of the domain to the codomain. So it sort of makes sense. All right. So somebody was typing earlier, but there's no new text in the text channel. All right, so let's move on then. So in addition to this observation, there's another important criterion for a subset of x, y, Cartesian product to be a function. In English terms, each element of the domain must be mapped to one and only one element in the codomain. So let me say that one more time. Each element of the domain must be mapped to one and only one element in the codomain when we are considering a function. Okay, so there's a lot of words, right? And most people look at this. If you're talking to an English major, okay, the English major would probably look at this and go like, yeah, I kind of get the idea. No, I don't think you actually get the idea, because each word is chosen for a particular reason. So when I use each, okay, it is a universal quantifier. In other words, every element in the domain, okay, must be mapped, which also means, you cannot have anything in the domain that is not mapped. You got to map every single one of those. And then the second one is also, to some of you and to myself, it is fairly clear what that means, but to some other people, it may not be very clear. Okay, what is the difference between one, versus one and only one versus only one? I mean, what is the difference? Well, one and only one means exactly one. In other words, you cannot have an element of a domain mapping to nothing in the codomain. You cannot have it mapped to more than one items in the codomain. It has to be exactly one thing in the codomain. So, as you can see, when I start to describe these concepts that really requires precision using a natural language like English, it gets kind of difficult. I really have to give you guys a lot of examples, like this one is not, this one is, and this one is not, in order to make it more clear. But there's another way to do this. Okay, so there's a bunch of stuff here. And then eventually we end up with this thing over here. So I'm skipping a lot of stuff just to get to this part here. So what does that mean? So let's take a look at this equation here, because I want to kind of reverse the whole thing. Because if you read the notes, I certainly hope you guys have read the notes. It's going forward for by constructing the statement that precisely describe what a function is. So instead of doing that, assuming you have read it, I'm going to reverse the process. I'm starting with the definition. I'm starting with the qualification of what a function is. F is a function in this case. And then I'm going backwards to analyze and break it apart to see what it means. All right, so I hope I will eventually get you some examples. Why don't we start with some examples? I think that is probably a better idea. So we'll start with some examples and then we will talk about that. All right, so we're going to start with examples. There we go. And in the examples, I am going, so I don't think I need to use, okay, so in all of these examples, the proposed thing is we are trying to consider whether f is a function. Mapping from x to y. Okay, so this is the question. Is f a function with a domain of x mapping to a codomain of y? But I can do better. I can do better than that. Instead of using x, which is kind of abstract, I am just going to give you a set, which is 1, 2, and if you want curly braces to appear as curly braces in LaTeX, you have to escape it first with backslash, because otherwise curly braces is actually used as part of the language of LaTeX. So so you have to remember to use backslash curly brace, open or close, in order for the curly brace to appear as curly braces, like that. Okay, so here's the question. So I'm asking, is f, as we'll define here, a function mapping from the domain, which is the set of just 1, 2, to the set of AB as the codomain? So that's the question. But we're going to have several examples to go through here. I see that someone is typing. Is such that right? I'm not even sure what that is referring to. So I am going to encourage you guys not to use pronouns. things like this, that, it, he, she, that sort of stuff, and instead, refer to exactly what object or what subject you are referring to. Because in a class like this, yeah, that can be confusing. Oh, the vertical bar is read as such that. That is correct. So quoting the vertical bar, can be helpful. And also we use the vertical bar, for cardinality too. So using vertical bar in this particular context, does it mean such that in that particular context? That would definitely help clarify what is being asked. Alright, so I'm going to give you guys some examples here, and I am not using LaTeX because there's no need to. So I'm going to give you an example of 1b and 2a and ask you, is that a function? Does it meet the requirement that every element in the domain is mapped to one and only one element in the codomain? Yeah, such that where those they both work. Alright, since there are no duplicates in the set, is the one and only one element in the codomain unique as well? Well, it's counting. That's all it's doing. It's just counting. One and only one means exactly one. It doesn't say anything about uniqueness. It's just counting. It's just saying, oh, it has to map to one and only one, which means one. But which one? Doesn't say anything about which one. Alright, so let's focus on this example here. Is this definition of f a function? In other words, I want to see if this is or isn't a function. Alright, so we have consensus from the two Jonathans. And in one of my other classes, I think I had two Nathans, which is coincidental, but just kind of interesting. The answer is yes, it is indeed a function. Very good. It is a subset. Okay, Jonathan Wong is correct. It is a subset of 1, 2, Cartesian product with AB, but in addition to that, it is also mapping each element in the domain, 1 and 2, to one and only one element in the codomain. So 1 is mapped to B, 2 is mapped to A. Yep, we're good. Alright, let's take a look at another example. So this time we have 1b and 2b. And the question is it is or isn't a function? Alright, so we have, that is all. Okay, so we have, okay. Alright, so this is interesting. Okay, it is a function. It is a function. Okay, so let me first state the answer, and then we'll talk about two things. Okay, so first of all, it is a function, and the second thing is, right or wrong in this class is not by voting. Now, I do want to get you guys to give me the answer, because if you guys are not getting the concept, I want to know it. Okay, because because this tells me I have further explanation of things. But in the case of exams and homework assignments and stuff like that, what is considered the correct answer is not by voting. In other words, the entire class can be wrong, and I would just mark everybody as wrong. There's no such thing as the majority of the answer is the right answer. That doesn't work in this class. I just want to make it very clear. This is a very good opportunity to say that. Anyway, it is a function because one and only one doesn't say anything about uniqueness. It doesn't say anything about that. So it is just counting. It's all it is doing is counting. It's counting and say, is one mapped to one and only one thing in the codomain? Yeah, it's mapped only to B. And then the next question is, what about the other element of the domain, which is 2? Is it mapped to exactly one thing in the codomain? And the answer is, yep, B is in the codomain, and 2 is mapped to B and only B, so it is one and only one. So it's okay. It is actually perfectly okay to be like this. Let's try the next one then. How about 1A, 1B, and then 2a. We'll make 2b. Why not? Okay, so is or isn't a function. Okay, so here's the question. We have no. Okay, so but now we have to explain why is it not a function. So you would probably want to think like that in your mind, because you're not just going to guess and go like, well, since the tag has already talked about what is, this is probably about what is not. Okay, that is not a good way to approach this. Okay, so you need to tell me why this particular definition of f as a set is not a function. Why? Which rule is it breaking? Because there's a rule in order for a function to be a function. So if you say something is not a function, it has to be breaking one of those rules. Which rule are we breaking? Yep, so if you look at it from the graphical perspective, it is breaking the horizontal line test. But in terms of how we define functions in this class, what rule is it breaking? 1 is no longer mapped to 1 and only one thing in the codomain, because 1 is now mapped to 2 things in the codomain, and 2 is certainly not 1. That is the problem. Exactly, so Adam is correct. Alright, so in this case, the correct answer is it is not a function. But remember, when you process things like this, you don't have to type in a text channel, but in your mind, it is important to think about why it is not a function. Okay, because leave nothing to chance. Okay, there's no such thing as, oh, I just got a lucky guess. Lucky guesses do not work very well in this class. So you have to be able to explain why it is not a function, because in the exam, I will ask for explanations. Okay, I will ask, okay, so if you think this is not a function, tell me why it is not a function. So you have to understand why something is not a function. Which rule is it breaking? And you kind of have to use the terms that we introduced in this class, so you cannot just say, oh, it broke the line test. Well, I never say anything about the line test in this class, horizontal line test in this class. So you have to use the terminology that we have talked about in this class to explain things. Okay, so here's another question. Let me fix the other one first. So this is no longer a question because we just answered it, but this one is still an answer. Is it a function or is it not a function as it is defined here? And if it is not, why it is not a function? Which rule is it breaking? Explain to me how it is not a function. Nope, it is not one to many. Oh, it is still, it's breaking the rule in 2 different ways. Yes, it is one to many, but it is also 2 is not mapped. So in this case, Wilson and Elijah are both correct. Okay, it breaks 2 rules instead of just 1, which is the previous one. Cool. So let me state the answer first. And then we have one more example to go. Okay, so we have f equals 2. I think I would like this one. 1a and 2c. What about that? And if it does break a rule, which rule is it breaking? Okay, C is not in the codomain, but that wasn't really how I stated the requirement. Which requirement did I state? That basically invalidates this particular f as a function. Jonathan is partially correct. It is not a subset, but a subset of what, right? So that's the question. It needs to be a subset of okay. Exactly. Subset of the Cartesian product. Very good. So this particular definition of f is breaking the rule. Well, you can call it breaking 2 rules. Okay, you can say that it has broken 2 rules because it broke the rule that 2 is not mapped to anything in the codomain, because by this notation, the codomain is AB, and 2 mapping to C is like, hey, that doesn't help because C is not a part of the codomain. But it also broke the other rule that we talked about earlier, which is it has to be a subset of the Cartesian product between the domain and the codomain. 2C is not an element of that Cartesian product. So it broke 2 rules again. Okay. See how this is kind of fun? Using these examples. Now, examples are great, when we are studying, but eventually you need to understand the abstract concept. In other words, examples are great when we are getting introduced to a concept to help us understand the concept. But once we understand the concept, we should be able to apply the concept to other things to solve problems without having to resort to examples again. So that would be the objective eventually. So this time we have 1a, 2b, and 3a. Yeah, I have to throw these things out here just so that you guys can go like, okay, it is not, and why is it, why it is, and why it is not. Okay. All right, so here we go. Here's the next question. What is the answer to this question and why? Okay, let me just type that out too so that you guys don't forget. Alright, there we go. Alright, so Nathan said, because it is not a subset of the Cartesian product. Very good. Alright, good job. That's it. Okay. Now, Owen said, 3 is not in the domain. It is true that 3 is not in the domain, but that was not, it wasn't a rule. Okay, the rule did not say anything about, the first thing in each 2 tuple has to come from the domain. It wasn't stated like that. So the rule that it broke was F is no longer a subset of the Cartesian product of the domain and the codomain. So this is, I know, it seems like I'm just nitpicking what you guys are saying, right? But it is important, okay? It is the same kind of nitpicking, that is necessary when you're talking about the syntax of a programming language. If you mistake and if you mistyped, okay, and use a single quote instead of a double quote when you are writing a C program, I mean, to a person, it kind of makes sense, right? Yeah, I kind of get what you mean. But guess what? The program is not going to compile. Or depending on the context, it may still compile, but it'll give you something that you're not expecting. So I'm nitpicking because I need you guys to think in terms of the rules and the definitions that are given to you. Okay, start with those. Okay, it is very important that you link your answers back to the rules and the definitions that we talked about in this class. Alright, so that is super duper important. Alright, so I think we have beaten this horse to death quite a few times already. So this is not a function, and the reason is it is not a subset of the Cartesian product between the domain and the codomain. Alright, so you can see how, the wording, can be really kind of confusing because, we have to use this many examples to illustrate, okay, I think we get what a function is. What about this notation here? What is it saying? It's really saying the same thing, except very short, and it is very short and very condensed. Okay, so we'll go ahead and take a look at this one here. Alright, so the first thing we want to know is where's the e coming from, the lowercase e? E is really just an element of the domain, because x, according to this notation all the way up here, x is the domain and y is the codomain. So we are just saying, if I pick any element out of the domain, the following should be true. What following are you talking about? this thing here. Okay, everything from this round parenthesis all the way to this round close round parenthesis all the way over here. That needs to be true for every element that I can choose from the domain. Alright, so we got a comment in a question in the text channel. The examples you gave are possible set representation of the function you stated. I'm not sure how I should interpret that particular sentence. Each subpart of a question is redefining f and is asking, if I define f like this, is it a function? If I define f like this, is it a function? If I define f like this, is it a function? But we are restricted by this particular notation here, which is f is supposed to be a function, mapping from the domain of 1, 2 to the codomain of AB. These are very specific definitions of the set f, and I'm asking, in this case, is it a function? No, it's not. In this case, is it a function? Nope, it's not. And so on. So that's kind of the intention of the examples. I'm not sure whether that answers Wilson's question or not. And there are 2 more people typing, so I'm going to pause a little bit. Okay, very good. So we got 2 more questions coming, and I'm going to wait a little bit. And now we got 3 people typing. Very good. I like interaction, so the more you guys type in the text channel, the better. And I think for a class like this, having a text channel works better than an actual physically face-to-face class, because in a face-to-face class, you guys cannot give me an example like you can type here. Alright, so the first one is, I'm having a slightly hard time reading the statement. For all E in X such that tuple EQ is in F is true. Okay, so I think Jonathan is referring to... Oh, you're referring to the same thing here. Okay, that's fine. Yeah, I'll get to that. There's cardinality in there. Yes, that is true. There's the cardinality, and we are comparing the cardinality to 1. That's what the 1 is for. Very good. Okay, so Adam is 100% correct. We are basically creating a set. You can call this an ad hoc, set. Basically, we are just creating a set, just so that we can do some comparison in this case. All right, very good. Oh, okay, got it. No problem. No problem. All right, the notes mention ad hoc a couple of times. So ad hoc simply means it is it's created on the fly for a purpose that's only important in this notation, and therefore it doesn't have a name. It doesn't take on a particular special name. Look at it as a local variable that has no use outside of a particular scope. That's it. Yeah, they are indeed the same. One is a infix notation, and the other one is used as delimiters, surrounding something. Only off by 1 hex val for color. All right, so the next question is, what are E and Q in this case? Okay, that's a good question. So E is determined from the outside. We are binding E to a particular thing in X, but we have to bind E to every single one in X, and this statement here in parentheses still has to be true. So E is determined from the quantifier. Q, on the other hand, is determined from the set notation. So Q is basically bound to, we are basically finding every single element in F that looks like this. Okay, it starts with whatever E we have chosen outside, and then it can be paired with any Q as long as the tuple E blah is in F. So we are basically looking at this thing here. I think it is best to give you an example. Okay, so an example probably works best. The universe by definition has everything in it. So there's no restriction as to what the universe has, and that's why we have this notation of for all E in X, okay, which basically means for all E in the entire universe, E as an element of X implies. So that's something that we talked about in the previous class. So the notation is just a little bit different in that case. Alright, so I think I can clarify this notation by the use of an example. So let me switch back to the mind map. I think I can put it in the mind map as a notation. So we'll go ahead and open a new point here, and we'll say example of the weird notation. There we go. So the first thing we do is we are going to create an actual set. Okay, so we're going to define F as A1, A2, and then B0. Okay, and then we'll go ahead and define X as A, B. Actually, just A is good, and it will define Y as 1, 2. Alright, so in this case, it is quite obvious that F is not a function. So the purpose is not really to determine whether F is a function or not, but to evaluate a particular, the ad hoc set notation that we are talking about. Okay, so to describe the ad hoc set, okay, so this time we have to use LaTeX. So assuming E equals to A, what is the following? Assuming this, okay, let me type it. Assume E is A, what is in the ad hoc set? So I'm going to use exactly the same notation in the notes. So we have EQ being describing an element in this ad hoc set here, such that EQ has to be an element of F. Close that and that. Okay, so assuming E has a value of A, in other words, we are binding the value of E in the quantifier to a specific element of A in the domain, in the X, which is the domain. What is this particular set? No, it doesn't have to be a function. The evaluation of this expression does not depend on the fact that F is a function. I just want to know what the ad hoc set is going to look like. And Jonathan is correct. Okay, so Jonathan is correct. So I'm going to put here, the answer is, it would be the set that has two elements. So E is A, so we are looking for the pattern of A blah. Okay, whenever we have an A blah in F, it belongs to this set that we are constructing on the fly. That's why I use the term ad hoc. Okay, so we have A1 being one of them, and then we have A2 being one of them. Is that okay? Oh, I see it is off screen. Now it is not. Is that okay? Does everybody understand why the answer to this question is a set that has two elements? Very good. So I'm going to do something lazy by copying and pasting. And you go like, so what are you going to paste this time? Okay, the answer part is not important here. So this time I'm just going to add 2 more things to this, and I'll get you guys to answer the question. Alright, so what is the answer to this question? It doesn't matter. It's not about the cardinality. It is about the notation, because I just want you guys to understand, the notation that was mentioned earlier. So what is the answer to this question? The answer is very good. All of you are correct. The answer is 2. So we are just basically working on the expression step by step, working from, once we fix, what E is, we are just looking for specific elements in F, okay, to put it into this particular ad hoc set, and then we are just counting how many things are in the ad hoc set. Okay, so the answer in this case is 2. So based on this, okay, is this definition of F a function? Is F a function? The question is. And if not, why is it not a function? It is not a function well, okay, B0 is the other problem, but if we just focus on A, it is not a function because it doesn't meet this requirement. The ad hoc set cardinality needs to be exactly 1, and in this case it is 2. So that's why it broke that rule. Okay, so let me just make this. There we go. So now, we don't have to consider B, okay, because the rest of this discussion remains exactly, is just as valid, okay? But I do want to use this opportunity to say no, because the cardinality is 2, not 1. There we go. So is this discussion okay? Is it clear, what I'm trying to illustrate here? And can we now understand what this whole notation is about? Yeah, exactly. That's why examples are useful to help understand a concept. But once we understand the more concise description in this particular notation, we want to kind of keep that in our mind. Even though the examples are helpful, this is the more concise way to describe something. All right. Okay, well, that's fine. I mean, that's why we have lectures, because it's kind of like textbooks, right? I mean, some textbooks can be very verbose, and they spell out all the possible cases. But guess what? A book is not interactive. A book cannot ask you and say, "Are we good here? Do we need some more examples?" Nor can it answer a question from you, which is basically like, okay, look at this F here. I'm coming up with an F, and this is supposed to be the domain, this is supposed to be the codomain. What are the characteristics of this thing here? Is it even a function? A book cannot answer that question, but I can. Well, you would hope that I can, right? Yeah, together it is a lot, and that's why we have this long weekend. All right, so let me give you another example here. Okay, so yeah, 1 is not enough, so let's go ahead and do another one. Let's see, what should I do here? Oh, I can do this. I am just going to modify X to include B. Okay, so I am going to insert a new node here. Oh, not here, not there, right here. So I'm going to say assume E equals to B this time, and I'm going to ask what is the ad hoc set. Okay, same thing that we were talking about earlier, EQ, whereas EQ is in F. And there we go. Oh, what am I missing here? Error setting the text for the following thing. Found a close. Okay, so I'm not closing the set notation correctly. There we go. Backslash. There we go. There we go. All right. So here's the question. if we are not binding E to A, because remember, we have to bind E to every single thing in the domain, and the statement still has to be true. So this time we are binding E to the other element because I changed the way I defined X. So what is this particular set here? Yep, I got a whole bunch of correct answers. It is indeed the empty set. Okay, so the answer is it is an empty set. So I'm going to repeat. I'm just going to say it here. Okay, what is the cardinality of the set that we have just constructed? If we are to put a cardinality operator, exactly, it is 0. Okay, the cardinality of an empty set is 0 because we are just really counting the number of elements. So because an empty set has no elements, then the cardinality is going to be 0. And exactly, so Jonathan read my thoughts. Okay, because 0 does not equal to 1, that's the other reason this particular setup is going to fail the test that f is a function. So are we good so far? Are we starting to understand what this notation is trying to say? Excellent. Very good. Very good. Well, as it turns out, we finished this module just in time for the next homework assignment, but I'm not ready to release it yet, so I'm going to have to spend the next hour or so kind of tuning a little bit in order to release it, but that will give you something to do over the long weekend. I know you guys want to use the long weekend for other things too, which you can, but it is important to keep, quote unquote, keep the engine warm. Okay, and that's what I'm going to do, is to give you an assignment to keep the engine warm over the weekend. All right. So, does anyone know, why it is important to keep an engine warm? Like we are talking about a gas engine here, not a electric car motor. Because I want to draw an analogy between what I'm talking about here. Because motor oil operates, best at a certain viscosity, and modern day motor oils would change the viscosity based on the temperature, and they're optimized to operate at a specific temperature range where the viscosity and the property of the motor oil will protect the engine the best. Cold is not good for engine oil. Too hot is not good for the engine oil. It has a very specific temperature range, and that's why, quote unquote, keeping the engine warm. Sometimes, you will say, but isn't it better to just turn the engine off, and just not having it to rotate and wear and tear? Sometimes, depending on the situation, it may be slightly better to keep it running, so that you can operate the engine and the engine oil at the temperature that they are optimal. And that's what I'm intending to do. Oh, the Blackbird is interesting. Oh, that I did not know, Wade. That's very interesting information. I just know that it leaks like there's no tomorrow when it is not flying, when it's on the ground, because it's counting on the heat expanding the metal to seal, the seams, and therefore stopping the leak. I did not know the engine oil is in the form of dust. That is interesting. Electric cars doesn't like extreme temperatures because of the battery. Okay, very good. So I am going to work on your homework assignment so that you have something to do over the weekend. It will be done tonight. Okay, so it will be released tonight, and you have until before lecture time next Wednesday to submit it. So once again, you can only submit it once. Okay, so don't rush through this one, and just go like, okay, I'm going to turn it in so I have a really nice long weekend. Spend your time, go slow, make sure you understand all the concepts. All right. So at this point, I think I can stop